can you copy down the title, probability expectation, and copy this down. This is the keynote. Expected result is the probability of an event times the number of trials. So basically what it's saying is, for example, if you were to flip a coin 300 times, what is your expected result? Well, the probability of an event, for example, heads, is a half, right? Well, it's 1 out of 2. You did it 300 times, so you do 1 out of 2 times 300. So you'd expect a head to come up 150 times. Now let's do a question. So you roll a fair dice. So fair dice is out of 6, 320 times. How many times would you expect a number higher than 4? Okay, so we know the probability is out of 6. Numbers higher than 4, so we've got 5 and 6, so that's 2 numbers. So the probability is 2 out of 6. Always recommend simplifying it to make the calculations easier. So it's a third. Now that's the probability is a third. That's this part here. Now you've got to times it by the number of times you do your trial. Well, this time was done 320 times. So you times it by 320. 1 times 320 is 320, and then 320 divided by 3. Okay, if you're not too sure about what the result is for this, remember use the bust up method. So if I do over here my workings, so 3's into 320. Well, 3 goes into 3 once, 3 goes into 2, 0. Carry the 2 because we didn't use it. 3 into 20, well, that's 6. And then there's still a bit left over, so you have to add a decimal place. Add another 0. So 3 into 20 was 6, remainder 3 times 6 is 18, so there's remainder 2, and it just keeps on going. So you would expect it 106.6 recurring times. So let's write that as my answer. So, I mean, you can't really have 0.6 recurring, so I round this up to 107 times. Okay, flip a biased coin. The probability of a tail is 0.25. How many times would you expect to get heads if you flip the coin 280 times? Okay, so the probability of a tail is 0.25, but it's asking for how many times would you expect heads. So the probability of tail is 0.25. Well, from yesterday's lesson, you know the tail plus the head have to add up to 1. So 0.25 plus 0.75 makes 1. So if I just write here, P for probability of heads is going to be 1 minus 0.25, what is 0.75. Now, to do this, you do the probability of the event, what's 0.75, times by how many times we did it. We did it 280. Okay, so you can either do 75 times 28 and then figure out the zeros at the end, and you've got the grid method or whatever method you need to work it out. Or you might see a little trick. 0.75 as a fraction is the same as 3/4. What makes it easier to do. So you can either do 280 times by 3 and then divide by 4, or you can do it the other way and get the same answer. 280 divided by 4. Well, 28 divided by 4 is 7. So you know it is 28 divided by 4 is 7. So if I put 7 here, we still got the 0, so it's 70. And we've divided by 4 now, so all we've got left to do is times it by 3. So your answer is 7 times 3 is 21. Add the 0, 210. So the amount of times you expect heads to come up would be 210. If you ever wanted to check it, you could do 0.25 times by 280 and make sure it equals 70, because once you add 210 to 70, it should come to 280. Okay, question 3. Now we've got a spinner here. We spin it 300 times. The probability of white or black is the same. So that's the key word there, the same. Now, if we fill the rest of this out, we did this last lesson as well, we know this whole grid here has to add up to 1. So I'm going to do my working up at the top. Let's add these two numbers, 0.2 plus 0.36. Okay, so they add up to, always easier to add the 0 here because it's like 20 plus 36 is 56, so it's 0.56. Well, you know it all has to add up to 1, so you do 1 minus 0.56. 56 plus 44 would make 1, so it's 0.44. Well, you know 0.44 is split between these two, and you know these two are the same. So you're going to have to half your answer. What would get 44 divided by 2 is 22, so 0.22, 0.22. Check it. Let's see if these all add up to 1. 44, 64, 90, 100. Yeah. So we know we've got that bit right. But that's not the question. How many times would you expect black? Okay, so black is here, 0.22. So if I do this here, we do probability of black is 0.22 times by how many times it was done? 300. Okay, so 22 times 3 is 66. Okay, because when I did 22 times 3, that's 66. Well, it's not 22, it's 0.22. So I'd actually times this by 100 here, right? But it's not 3, it's 300. So it actually divided this by 100. Well, because I times this by 100 and divide this by 100, it just cancels out. So it's just 22 times 3 was 66. So that is your answer. Okay, now I'd like to do some practice questions. So go to Hegarty Maths, and what I'd like you to do is 355 at Hegarty Maths. Thank you. Okay, put down the title Experimental Probability. Experimental probability is just kind of like real life scenarios for probability. So can you get this down? This is the equation you need to know. Experimental probability, also known as relative frequency, is the number of times the result occurs divided by the number of times the experiment is done. Okay, so, and the most important thing about all of this is the more times the experiment is done, the more reliable this is, this experimental probability. Okay, so if I look at it in terms of questions and real life scenarios, we'll go from there. Question 1. Bob and Bill play 42 games of chess. Bob wins 12 games. So we know Bob wins 12, it's 42 in total, so we also know that Bill won 30. Now, with experimental probability, they always use the word estimate. The reason it's an estimate is not because you're guessing, but because you're basing it on the experiment results. So the probability that Bob wins, well, we know Bob wins 12 games, and it is out of a total of 42. So that is his experimental probability. Now you always got to simplify, divide by 2, so that is 6 over 21. Probability that Bill wins, well, Bill is, he didn't tell you how many, so it's 42 in total, minus how many games Bob won was 12, so we know Bill wins 30. So the answer is 30 out of 42, divided by 2, what's 15 over 21. So even though it says estimate, don't guess, you still just use the numbers that they give you to work out the probability. Number 2, biased dice is rolled 60 times, here are the results. Estimate the probability of a prime number. Those who can't remember what prime number is, can you make a note? It is, a prime number is any number that only has 2 factors. So 2 factors is 1 and itself. Well, 1 is not prime because it only has 1 factor. 2 is prime because the only factors of 2 is 2 and 1. So that's one of the prime numbers. Here 2. 3 is prime because it's 3 and 1. 4, not prime because 2 goes into it. 5 is prime. 6 is not prime because 2 and 3 go into it. So we're looking at the 5, 7, and 7. So estimate the probability of a prime number. Okay, so all you have to do is these are the prime numbers. You're going to have to add up the amount of times they each came up. So add up the frequencies. So 5 plus 7 plus 7, what is equal to 19? Well, that's how many times it came out, but it's out of 60. So 19 out of 60 is your answer. Estimate the probability a factor of 8. Okay, so many ways you can work out the factors, but it's the numbers that go into 8. So you know 1 times 8 is a factor, 2 goes into it, and 4 goes into it, and obviously 8 as well. So these are your factors numbers. So if I circle them in blue, we're looking at 1, 2, 4, and 8. There is no 8 on a dice. Okay, so these are the numbers 12, 5, and 9. So 12 plus 5 plus 9. Okay, 12 plus 5 is 17, plus 9 is 26. Okay, and it's again out to 60. Even numbers, divide by 2, 13 out of 30. That is your estimate. So estimate is just a word they use for experimental probability questions, but you still just work it out using the experiment results they give you. Okay, question 3. And both of these, question 1 and 2, they might also ask you, how could they make this experiment more accurate? Well, instead of rolling 60 times, they could roll 1,000 times or even 1,000,000 times. The more times you do it, the more accurate the results are. So it's always, when they ask you that question, is do the experiment more times, roll the dice more times, etc. But if you just write do the experiment more times, you're going to get 4 marks. Okay, question 3. Bob and Bill test a coin. Now, you've got to work out using, so Bob, he flipped a coin, number of flips is 450, and he got tails 175 times. Bill, he did 30 flips of a coin, had enough, and he got 12 tails 12 times. So look at Bob's. This is Bob's results here. Bob's estimate, and the question will say, what's Bob's estimate for example, tails, right? Well, you look at Bob's, the number of tails he got was 175, and it's out of how many times he did it. What's 450? Well, always simplify. If they both end in 5, very good chance it's going to be divisible by 5. Okay, but let's test. 5's into 175. Okay, I'm going to put my working over here. Bus stop method. 5's into 175. 5's into 1, 0, carry the 1. 5's into 17. 3, remainder 2. 5's into 25 is 5. So we know that is 35. 5's into 45. Well, 5's into 45 is 9. So it's 35 over 9, and you still got the 0, 90. Well, if it ends in a 5 and a 0, it's probably divisible by 5 again. So 5's into 35 is 7, and 5's into 90. Okay, well, 5 goes into 9 once, remainder 4, so 5's into 40 is 8, so it's 18. Okay, so that's your results. Bob's estimate for tails. Well, let's look at Bill's estimate for tails. His is 12, because he's at 12, and it's out of 30. What simplifies, divided by 2 into 6 over 15. Who is more accurate? Well, if you're looking at these, the more accurate one is always the person who does the experiment more times. Bob the experiment more times, so the answer is Bob. Bob is more accurate. Okay, now I want you to practice some questions on this. So go to Hegarty Maths and do questions 3, 5, 6. Task 3, 5, 6 on Hegarty Maths.